Kia ora Year 12 and 13. Here's the second part of the first question from the last year's integration exam. So there are two questions in this. The first one is a merit question and the second one is an excellence question, and we've covered both of them in class now. Okay, the first question is this. Use integration to find the area enclosed between the curve y equals 5x minus 3 over x plus 3 and the lines y equals 0, x equals 2 and x equals 5. And there's the curve. The area is shown shaded in the diagram below. So what we're looking for, we'll call it A, is the integral between the limits of 5 and 2 of this function, 5x minus 3 over x plus 3 dx. Now we can rewrite that into this form. So something over x plus 3, so let's look at that 5 and say, how can I match this up, 5, to get 5 over x plus 3 with some left over, because that's going to help me simplify. So what I've done is I've forced 5x minus 3 to be 5 times x plus 3 to match up, but now I need to take away 18, right, because 5 3s are 15, but I want to end up with minus 3, right, we did that in class. So here I'm going to have, in my numerator, I'll have this dx. Okay, I'm going to pop a new slide in here, but you should be able to go pretty easily from this point on. Alright, so we've got to A equals the integral between 5 and 2 of 5 minus 18. So we can split this into two bits, the integral between 5 and 2 of 5 minus 18 over x plus 3 dx, and that anti-differentiates to give me 5x minus 18 times the log of x plus 3. And that's between 5 and 2. Now we just have to evaluate that. So we're going to get 25 minus 18 log 8. Right, I'm substituting in 5 into here and here. Minus 10 minus 18 log 5. Simplifying that down, we get 15 from those bits, minus 18 log 8, plus 18 log 5. Now some of you are going to pull your calculators out at this point, and that's fine, but we can simplify a bit further, and we get 15 plus 18 log 5 over 8. And that ends up as giving me 6.54 to 2 dp. Okay, so that's a merit question. So really the only thing that's tricky in there is making sure that you can do this step here where we rewrite so that we match up the denominator with a factor in the top line, with a matching factor in the top line. It's a little bit like what we do when we do completing the square. Alright, on to the next question. So this question is about something called a volume of a solid of revolution, and they used to be taught at level 3, but now they're not really taught. So what the exam paper last year did is it put an example in, but it basically told you exactly how to do it. So first of all, let's read this. Consider the curve defined by the function y equals f of x, so that's it here, so any old curve, bounded by x equals a and x equals b. So we're quite used to this. Right, but we're used to finding the area under that curve. Now, on to the next slide. It's going to tell us about the new thing. This portion of the curve, so there's my curve, that's my f of x, is rotated around the x-axis as shown below. So what I want you to imagine is that curve being turned around, here we go, maths with bad drawings. Okay, so it's being rotated around the x-axis. and this creates a three-dimensional shape. So the volume created by this rotation is given to us by this formula. So volume is equal to pi times that integral there. You can probably see where this is going. So now we're given a specific function and we're going to do this to it. So this function is y equals cos of x, and we are going to rotate that function around the x-axis between these two values. So we have to find the volume created by this rotation. So I'm going to start a new slide here, and what we're going to be doing is just substituting in to get v is equal to pi between the two limits of f of x squared dx. Now I'm going to teach you how to do this in class as well, so if you're watching this video soon, we won't do this yet, but you can do this exam question just from substituting into the formula, and you can probably see what's going on in here just by looking that this here is my radius, and that radius length is given by the value of the function. So there's not really that much mystery to these, and they're very, very cool. So we will spend a wee bit of time on them. Now what you can do now is try to just substitute things in here. So we've got our pi here, we've got our limits at pi on 2 and 0, and our function is cos of x. We need to square that. So have a go at evaluating that integral, and I'll go through it on the next slide. Okay, so v is equal to pi times this. So cos of x squared is the same as cos squared of x dx, and you'll remember, hopefully, that the incredibly useful trig identity of cos 2x will pop up with this. Right, so you're going to be using that in this question. We want to rewrite that with cos squared x as the subject. So we're going to have cos squared x equals cos of 2x plus 1 over 2. Right, now we're going to take this and we're going to pop it into here, and we'll be done very soon. So we get v is equal to pi times the integral between pi on 2 and 0 of 1/2 plus 1/2 cos of 2x dx. So you have to say this is a lot easier than excellence questions we've encountered in differentiation. Well, I think so anyway. So this will be x on 2 plus, taking a look at this, what differentiates to give me cos? Well, it's sine. So it would be sine of 2x, matching up that angle. Now, if I want to end up with 1/2 here, I'm going to be pulling out a 2 here, so that needs to be, 1/4, evaluated at pi on 2 and 0. Now, if you got as far as this, that was merit. So actually, the excellence bit is actually pretty straightforward. All we have to do now is some substitution. Okay, so let's see where we've got to. We've got equals pi times x on 2 plus 1/4 sine of 2x. Like that. Now if I want to be more elegant, I could pull out the 2 here as a factor out here, but I'm not going to. Okay, so now I'm substituting in, and we get pi times, right, half of pi on 2, so that'll be pi on 4, plus 1/4 sine of, right, 2 times pi on 2, so it'll be 2 pi on 2, which is pi, minus 0 plus 0 equals pi squared on 4, and sine of pi, remember, sine of pi is just 0, so it's pi squared on 4 plus 0 minus 0. So my answer is just pi squared on 4. Okay, so just leave it like that. And approximate answer is 2.467. Alright, so that's an excellence tick if you got down to here. Thanks for watching. Let me know if there are any technical glitches as usual.